Online payment fraud detection using machine learning in Python. This lesson introduces you to detecting online payment fraud with Python. Fraud detection is vital for keeping online transactions safe. You will learn to load real data, clean it, explore it, and build a model. No prior experience is needed. All steps are explained simply. You will use real-world tools like pandas and scikit-learn. Together, we will uncover how machine learning can spot suspicious transactions. Let us get started. Running the cell now. What you will learn in this lesson. How to load a credit card fraud dataset into Python. How to prepare the data for analysis. How to explore patterns in fraudulent versus normal transactions. How to train a machine learning model to recognize fraud. How to check model accuracy and important warning signs. How to make predictions using your own sample values. The real-world impact and challenges of fraud detection. How to keep learning with free resources and the YouTube channel. Running the cell now. For your comfort, we suppress warnings so you are not distracted. This helps you focus only on what matters. Always suppress warnings for a beginner-friendly experience. Import warnings, warnings.filter warnings, ignore. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. This code sets up a clean and consistent environment by suppressing warnings and fixing the random seed for reproducibility. Although there's no visible output here, these steps ensure that future data processing and model training will run smoothly and produce stable, repeatable results, an essential foundation as we begin exploring and analyzing the credit card fraud dataset. The code above means Python will hide most warning messages. It is important for beginners because warnings can feel confusing or scary. You are still safe and everything will work as expected. Let us now load our dataset. Let us load a real-world credit card transaction fraud dataset. We use pandas to fetch the data by only providing its public URL. You do not need to download anything manually. Data setup. Import pandas as PD. URL equals https://storage.googleapis.com/download.tensorflow.org/data/creditcard.csv. df equals pd read_csv URL. Print df.shape. Print df.head 3. Running the cell now. This output shows the initial loading of the credit card fraud dataset, revealing it has 284,807 rows and 31 columns, including anonymized features, V1 to V28, transaction amount, time, and the class label. Notice the variety of scaled feature columns alongside the target class, which indicates fraudulent, 1, or normal, 0, transactions, key for training our fraud detection model. This confirms the data is ready for exploration and analysis of patterns between normal and fraudulent transactions. You just loaded a real dataset of credit card transactions. Each row is a transaction, and fraud is marked as class 1. The shape statement shows how many records and features you have. The head preview helps you see the first few rows for inspection. Understanding how the data looks is always the first step. What is in the credit card fraud dataset? Each row stands for a single transaction. The columns are anonymized numerical values, V1, V2, etc. The amount to column shows the amount of the transaction. The class column is the target, 1 means fraud, 0 means normal. This is a real-world, imbalanced dataset. Frauds are very rare. You will learn special tricks to work with this kind of data. Running the cell now. It is good practice to see if your dataset has missing values. Missing data can affect both your analysis and model. Let us count all empty entries in the data. Let us check for missing values. Print df.isnal.sum.sum. Running the cell now. The output 0 tells us there are no missing values in the entire credit card fraud dataset. This is important because it means our data is complete and we won't need to handle or impute missing entries before training a model. Checking for missing values is a crucial first step in data cleaning and quality assessment. The result tells you how many missing values there are in total. If you see a 0, there are no missing values to worry about for this data. If there were any, you would need to clean or fill in the gaps. This makes your analysis more reliable. It is important to check how many fraudulent and normal transactions there are. Fraud datasets are usually imbalanced, frauds are much less common. Take a quick look at class distribution. Print df class.value_counts. Running the cell now. This output shows the distribution of normal versus fraudulent transactions in the dataset, with a vast majority, 284,315, being normal and only 492 flagged as fraud. Notice the severe class imbalance, which is crucial to consider when building models, as the rarity of fraud cases can impact detection performance. This quick check helps set expectations for the challenges ahead in identifying fraud. This output shows the number of normal, class 0, and fraudulent, class 1, records. Having very few fraud examples is normal and realistic. Imbalanced data is common for problems like fraud detection. You will learn methods to handle it soon. A simple plot can make it easier to see the difference in class sizes. Let us use Seaborn to create a count plot. Matplotlib is used to show the chart window. Plot class distribution. Import matplotlib.pyplot as PLT. Import Seaborn as SNS. SNS.countplot, x equals class, data equals df, palette equals set2. PLT.title, transaction type counts, 0 equals normal, 1 equals fraud. PLT.show. Running the cell now. This plot shows the count of normal, 0, versus fraudulent, 1, transactions in the dataset. Notice the large imbalance, with far fewer fraud cases than normal transactions, highlighting the class imbalance challenge in fraud detection. Understanding this distribution is key for selecting and evaluating appropriate models later in the lesson. This chart visually shows how rare fraudulent transactions are. Most real datasets have far more normal transactions than fraud. This big imbalance is a key challenge in fraud detection. You want to know if fraud amounts look different from normal purchases. Group statistics help you spot useful patterns. Summary stats for fraudulent and normal transactions. Print df.groupb, class, amount.describe. Running the cell now. This output compares the transaction amounts between normal, class 0, and fraudulent, class 1, transactions. Notice that while there are many more normal transactions, the average amount for fraud is higher, and the distribution shows greater variability in fraud amounts. This helps highlight potential differences in spending patterns that could aid in fraud detection. Look for differences in average, mean, and spread, STD, of amounts between the two classes. Sometimes frauds have higher or lower amounts. This can help your model learn important patterns. Feature understanding and selection. All features except for time, amount, and a class are anonymized because of privacy. You can build a strong model using these features. Removing the time column may help, as it is not always useful. The amount column sometimes gives away large suspicious transactions. Running the cell now. To focus, you will drop the time column. This reduces distractions during the rest of the analysis. Drop the time column just to keep things simple. df equals df.drop, time, axis equals 1. Running the cell now. Here we've removed the time column from the dataset to simplify our features, following the lesson's suggestion that time might not add much predictive value. This step helps focus the model on the anonymized features and amount, which are often more relevant for detecting fraud. Notice how this reduces feature complexity while retaining key information for better model performance. Your data is now cleaner and easier to work with. You are ready to move to pattern analysis and model building. Numeric values that vary a lot, like amounts, can bias machine learning. Standardization centers the numbers to help the model learn. You will create an amount_scaled column and remove the original. Scale that amount column for fair modeling. From scikit-learn preprocessing import standard scaler. df amount_scaled equals standard scaler .fit_transform df amount. df equals df.drop amount axis equals 1. Running the cell now. Here, we've standardized the amounts feature to ensure it scales similarly to other features, improving model performance. Notice we've created a new column amount_scaled and removed the original amount column to avoid bias from differing scales. This step is crucial for fair modeling since transaction amounts vary widely and can disproportionately influence the model. Amount_scaled means the values are now centered around 0 with equal spread. This helps learning work better and avoids giving extra weight to transaction size. Visualizing distributions for each class can highlight differences. Kernel density plots show how transaction amounts vary for fraud and normal events. Visualize feature distributions for fraud and normal. SNS.kdplot, df, class equals 0, amount_scaled, label equals a normal, fill equals true. SNS.kdplot, df, class equals 1, amount_scaled, label equals fraud, fill equals true. plt.legend. plt.title, distribution of scaled amounts. plt.show. Running the cell now. This plot compares the distributions of scaled transaction amounts for normal and fraudulent classes. Notice that fraud transactions tend to occur more at higher amounts, which suggests that the amounts feature can be a strong indicator for fraud detection. This insight supports the lesson's point about leveraging amount while carefully considering other features like time. The blue area shows normal transactions. The orange or red area shows fraudulent ones. Sometimes frauds cluster around certain values. Visual differences in shape can help models separate frauds from normal events. You must divide data into training and test sets. Training tells the model how to learn, and testing checks its skills. Stratify keeps the same fraud to normal ratio in both sets for fairness. Split the dataset into train and test sets, 80% train, 20% test. From scikit-learn.model_selection import train_test_split. X equals df.drop, class, axis equals 1. Y equals df, class. X_train, X_test, Y_train, Y_test equals train_test_split, X, Y, test_size equals 0.2, random_state equals 42, stratify equals Y. Print x_train.shape, x_test.shape. Running the cell now. This output shows the shapes of the training and test datasets after splitting, with 227,845 samples for training and 56,962 for testing, each containing 29 features. Notably, the class column was removed to separate features from the target, aligning with the focus on feature selection. This split ensures a balanced distribution of classes, allowing us to effectively train and evaluate models using the anonymized features plus time and amount. You now have new variables for features and labels, split into train and test samples. Checking shapes makes sure nothing was lost. You are ready to try machine learning. Choosing a machine learning model. For fraud detection, you often use algorithms like random forest, logistic regression, or support vector machine. Here, random forest is a common beginner-friendly choice. It works well when you have many features and want to spot tricky rules. Random forest uses many small decision trees and averages their answers. This reduces mistakes. Running the cell now. You will use the random forest method to train your fraud detector. Setting n_jobs to -1 makes it use all CPU cores, so it trains fast. Fit means the algorithm learns patterns from your training data. #train a random forest classifier on training data. From scikit-learn.ensemble import random forest classifier. rf equals random forest classifier, n_estimators equals 100, random_state equals 42, n_jobs equals 1. rf fit, x_train, y_train. Running the cell now. This output confirms that the random forest model has been successfully initialized and trained with 100 trees, using all CPU cores for efficiency. Notice how setting random_state equals 42 ensures reproducibility, so results remain consistent across runs. This step is crucial as it prepares the model to capture complex patterns in the fraud dataset, aligning with our goal of leveraging random forest strengths in detecting tricky fraud rules. Your model is now trained. It has examined regularities and differences between fraud and normal samples. Now you can test its power on invisible fresh examples. Now let the model make predictions on the test data. These are new transactions it never saw. Your model uses what it learned to classify if each test transaction looks fraudulent or not. #predict labels for your test set. y_pred equals rf predict x_test. Running the cell now. The code generates predictions using the random forest model on the test data, though no text output is shown here. The key point is that these predictions summarize what the model believes are fraud or non-fraud cases based on learned patterns. This step sets up evaluation and shows how the random forest applies its ensemble of trees to make final calls. You have created a new set of predictions. The model has guessed which cases are frauds and which are normal for the test part. Next, let us see how well it did. Raw accuracy alone is not enough if there are many more normal than fraud cases. Precision, recall, and the confusion matrix are more important for rare events. Recall shows how many actual frauds were detected. Precision shows how many predicted frauds were truly frauds. A confusion matrix breaks down mistakes in easy-to-read numbers. #evaluate results, accuracy, recall, and confusion matrix. From scikit-learn.metrics import classification_report, confusion_matrix. Print, classification_report, y_test, y_pred, digits equals 4. Print, confusion_matrix, y_test, y_pred. Running the cell now. This output shows the evaluation of our random forest model on fraud detection, highlighting very high precision and recall for the majority class, non-fraud, and strong, though lower, recall for the minority class, fraud. The confusion matrix reveals most fraud cases are correctly identified, but some are missed, 17 false negatives, which is important to consider when choosing and tuning models for critical tasks like fraud detection. This underscores how random forest balances accuracy across many features while emphasizing the trade-off in catching rare but important fraud cases. Look at recall and precision for Class 1, fraud. High recall means you detect more of the fraud cases. High precision means you make fewer false alarms. A real fraud system must always try to balance these numbers by design. A confusion matrix heat map lets you quickly see correct and wrong predictions. True frauds detected are lower right. Missed frauds are lower left. #visualize confusion matrix for clearer understanding. Import numpy as np. cm equals confusion_matrix, y_test, y_pred. sns.heatmap, cm, anat equals true, fmt equals d, cmap equals blues, exticlable sad smiley a normal, fraud, iticlable sad smiley a normal, fraud. plt.xlabel, predicted. plt.ilabel, actual. plt.title, confusion matrix. plt.show. Running the cell now. This confusion matrix visualizes how well the random forest model distinguishes between normal and fraud cases. Notice the counts on the diagonal represent correct predictions, showing the model's accuracy, while off-diagonal cells highlight misclassifications. This helps evaluate how effectively the model detects fraud without too many false alarms. Check the plot for how many correct fraud and normal predictions there are. Dark squares on the diagonal mean better accuracy. Off-diagonal means mistakes, which real systems always try to reduce. Knowing what features matter most helps you understand fraud. Random forest shows feature importance scores automatically. Let us plot the 10 most important features for your model. See the top features that help detect fraud. Importances equals rf feature underscore importances underscore. Indices equals np.argsort, importances, dash 10 happy smiley, dash 1. plt.figure, fig size sad smiley 84. sns.barplot, x equals importances, indices, y equals x.columns, indices, orient equals h. plt.title, top 10 important features in fraud detection. plt.show. Running the cell now. This bar chart highlights the top 10 features that the random forest model found most important for detecting fraud, ranked by their influence on the prediction. Notice how the model focuses on a few key variables rather than all features equally, showing that it captures specific patterns useful for distinguishing fraudulent cases. This helps us understand which data points the model relies on, guiding feature selection and interpretation in fraud detection tasks. The bars show which features your model relies on most for fraud decisions. These clues can guide banks, developers, and researchers. In business, important features might mean where to put stronger checks. Now let us see your model in action on a real-world-like case. You take a random transaction from the test set and ask for a prediction. Try your model on a custom made-up transaction. Sample equals x underscore test dot sample 1, random underscore state equals 1. Prediction equals rf predict sample. Print fraudulent if prediction 0 equals 1 else normal. Running the cell now. The output normal shows the random forest model's prediction for a single, randomly chosen transaction from the test data. This aligns with the lesson's focus on using random forest to classify transactions as fraudulent or not based on multiple features. Notice how the model can quickly label a new example, demonstrating its practical use in real-time fraud detection. The print statement tells you instantly if the sample was detected as fraud. This could be used in the future for reviewing real transactions. Try using your own custom details to check how the classifier answers. Let us make it interactive. You can type your own values for each transaction feature. You will get an instant fraud or normal prediction. Interactive prediction, enter your own transaction details. Inputs equals. For colin x.columns. Val equals float, input, f enter value for col. Inputs.append, val. Custom underscore pred equals rf predict, inputs. Print, fraudulent if custom underscore pred, 0, equals 1 else normal. Running the cell now. This output shows the result of your custom input fed into the random forest model, predicting the transaction as normal. Notice how the model classifies based on the combined patterns it learned, reflecting the lesson's focus on using random forest to handle complex feature interactions in fraud detection. This interactive step helps you see how your transaction details influence the final decision. Try small or large values for sample features. This helps you explore what types of data are flagged as fraud. It could be expanded later for real-time monitoring. Pause here and play around as long as you want. Real-world challenges and model limitations. Fraudsters keep inventing new tricks and patterns. A model trained on past data can miss new, unseen fraud methods. Transaction data may have errors, noise, or missing values. Class imbalance means that even high accuracy can hide missed frauds. Human oversight and constant model review are crucial. Running the cell now. What to try next? Expand your learning. Try other models such as logistic regression or support vector machine. Explore feature engineering like adding rolling averages or time gaps. Use advanced techniques for imbalanced data, such as SMOT or cost-sensitive learning. Visualize individual transaction paths for suspicious cases. Look for new open datasets on fraud or anomaly detection. Search YouTube for video follow-ups and step-by-step guides. Comment below what topic you want next, and subscribe for more practical data mining lessons. Running the cell now. Lesson recap. You learn to load and inspect a real payment fraud dataset. Clean and prepare data for safe modeling. Explore patterns and understand class imbalance. Train a random forest fraud detection model. Test and visualize how this model performs. Make manual and automated predictions. Understand real-world model limitations. Find resources to grow your skills. Thank you for learning with us. Do not forget to like and subscribe for new data mining in Python videos on YouTube. Running the cell now.